Assalamu alaikum and welcome everyone to Unit 5 of our database system course. The topic for this unit is relational model and relational algebra. Why is this topic important? The relational model is the foundation of almost all modern database management systems such as Oracle, MySQL and SQL Server. Understanding this model helps us how data is organized, stored and retrieved in practice. We will also discuss relational algebra, which provides a mathematical basis for querying databases. So this unit gives you both the theoretical foundation and the practical insights. In this unit, we will cover four main parts: relational model concepts, the characteristics of relations, integrity constraints and relational algebra. There are two programs in this unit. In this program, we will discuss first three, and in the second program, we will discuss relational algebra. In the relational model, the term attribute simply means a column in a table. Think of a table as representing a real world entity. For example, the entity student. Each property of a student, such as roll number, name, address, email, program, gender, phone, courses enrolled and semester is represented as an attribute. So whenever you see the word attribute, just think column adding of the table. But remember, unlike columns in a spreadsheet, which may allow all kinds of values in databases, each attribute usually has a defined domain, meaning a set of valid values. Now let's talk about tables. In the relational data model, data is stored in the form of tables. A table has two key components, rows and columns. Rows, also called tuples, are records. In rows there are records. Columns, also called attributes, representing properties of the entity. For example, in the student table, each row corresponds to a single student record. Each column corresponds to a specific property of that student. This table format makes data organization very intuitive and easy to query. A tuple refers to a single row in a table. For example, let's consider one row from the student table. As given, there are three records or three tuples. In 101, the student name Saima Rafiz enrolled in BScs. In this semester, they enrolled 3401 and 3403, and she belongs to from Rawalpindi. So that's a complete tuple. We can say this is a tuple or a record. We can use two terminologies for this: record or tuple. In the second row, Hina Ahmad record is available, and in third row, Muhammad Ali enrolled in data science, and the courses are 3505 and 6922 and belonging from Islamabad. This entire row is a tuple. It contains one complete record about a single student. So to remember it simply, attribute is equal to column, tuple is equal to row. Then a relation schema. Relation schema is like the design or blueprint of a relation. It defines how the table is structured before we even insert any data. It includes two main parts: the name of the relation, this identifies the table, and the set of attributes. These are the columns of the table, each with its own name and data type. For example, there is a table, namely customer table, having columns or attributes customer ID, customer name and status. These are all attributes or columns, and overall this is called schema. This schema tells us the table is named customer. It has three attributes. First one is customer ID, second one is customer name, and third one is status. At this stage, we are not concerned with actual rows of the data. We are only concerned with how the table is defined or look alike. You can think of the schema as the blueprint of a house. It shows where the rooms means attributes will be, but not who will live in them is called basically tuples. Then the degree of a relation refers to the total number of attributes or columns in the schema. For example, if the customer table schema is customer having customer ID, customer name and status, here there are 3 attributes, namely customer ID, customer name and status. So the degree of this relation is 3. Another example, a student relation might look like student table name, so its attributes are roll number, name, address, email, program, enrolled, semester, phone number. So these are 7 attributes. We can say in simple terms, degree is equal to number of columns or attributes in a table. Then the cardinality, which we will cover next, that is equal to number of rows in the table. So number of rows we can see after the implementation of the database. When user insert the data, how many number of records are there is basically its cardinality. Now let's talk about cardinality and columns. The cardinality of a relation means the number of rows or tuples it contains at a specific time after the implementation. For example, if the customer table currently has 50 rows, its cardinality is 50. If a table of student having 509 records, its cardinality is 509. If new customers are added tomorrow, the cardinality will be increased. If new students are enrolled or added, so its cardinality will be changed. On the other hand, a column refers to all the values of a particular attribute. For example, in the customer table, the customer name will contain the names of all customers like Ali, Sarah, Saima, etc. The customer ID column will contain all unique IDs. So we can summarize, cardinality is equal to how many rows the table has, and degree, how many columns the table has. Column is equal to the set of all values under one attribute. Then a relation instance represents the actual content of a relation at a particular moment in time. You can think of it as a snapshot of the table's data. For example, if today the student table has 200 enrolled students, that's the current relation instance. If 10 more students enroll tomorrow, the relation instance will change, even though the schema remains the same. Some important points: relation instances must not have duplicate tuples. Each row must be unique. This uniqueness is enforced by keys. A relation key is one or more attributes that uniquely identify each row. For example, in the customer table, customer ID can be the key because no 2 customers can have the same ID. It's always unique. We can say it a primary key. In the student table, roll number or registration number is the natural choice for a key. If a relation had no keys, it would be impossible to distinguish between 2 identical rows. Means records can be replicated, which would break the relational model's rules. Let's take an example of a customer. There are 3 attributes: customer ID, customer name and its status. So if customer ID is a primary key, we can't replicate this. There may be another record, a customer name again is Google and its status is active. However, we can't use the customer ID again. If we want to store this record, there should be customer ID number 4, 5 up to n. So we can't use replicated values for primary key. From this table, we can identify 3 important concepts. The relation name is customer, degree is 3, since there are 3 columns. The cardinality is also 3 because there are 3 rows or 3 records. Another important property, the order of tuples does not matter. We can store the first record towards fourth, towards third. Even if we can change the place of these records. It doesn't matter. Even if we rearrange the rows, it is still the same relation because a relation is a set of tuples. And remember, in mathematics, sets don't care about order. So the customer relation demonstrates how schema, degree, cardinality, and uniqueness all come together in a real table. One of the most important rules of the relational model is that a relation cannot contain duplicate tuples. This means every row in a relation must be unique. Basically, primary key ensures the uniqueness of every record. No two rows can have the exact same values for every attribute. For example, in a student relation, you cannot have two rows that both says student ID 1001, name Ali Khan from Islamabad, email is ali@gmail.com, is enrolled in BScs, is a male, and having mobile number 03 so and address and semester 6th. So we can't replicate. All other values can be replicated except primary key. Primary key uniquely identify the record. If duplicates were allowed, we would lose the ability to identify data accurately. Maybe we are inserting the records of Ali. So maybe in first go we insert the date of birth of Ali is 82, and in second go we may insert 83. So it's mean one record is correct and the other is not. That's why database system enforce keys such as primary keys to make sure each tuple is unique. Another key property of the relational model is that all values must be atomic, which means indivisible. You can't store multiple values inside a single cell. For example, courses in a courses column, we can't store math, physics, chemistry. That's always wrong. The correct way is either list one course per row or create a separate table for courses. This rule ensures that the database is easy to query because each cell contains exactly one value. Also, the relational model allows a special value called null, which represents missing, unknown, or not applicable data. For instance, if a student's phone number is not provided, we can set it to null rather than leaving it blank or using a fake number. Then the integrity constraints these are rules that make sure our data remains valid, consistent, and meaningful. They prevent errors when inserting, deleting, or updating data. For example, in a date column, we can't insert characters. Another example, you can't enroll a student in a program that does not exist. You cannot have a student without a roll number. Think of integrity constraints as the safety checks of a database system. They protect the quality of data. For example, if a person want to apply for identity card or national identity card, his age must be greater than 18. So that's a check. We can insert these types of checks on databases. Integrity constraints fall into 4 categories. These are inherent model based constraints, schema based constraints. Inherent model based constraints are built into the relational model itself. Schema based constraints defined directly in the database schema. Then the application based constraints, these are enforced by application programs. And the fourth one, data dependency constraints. These are used in database design and normalization. In the next slides, we will explore each of these categories in detail. Inherent constraints are rules that are part of the relational model by definition. These are not optional. They came automatically with the model. Example includes schema-based constraints. Schema-based constraints are specified in the database schema using data definition language. Data definition language are basically rules that the DBMS enforces automatically once they are declared. The main types of schema-based constraints are domain constraints, entity integrity, referential integrity, key constraints, and null constraints. Together, these form the backbone of relational database rules. A domain constraint specifies the set of valid values for an attribute. For example, the attribute age must be a positive integer. The attribute gender must be either male or female. The attribute email must follow a proper email format. These constraints make sure that only meaningful data enters the database. Without domain constraints, someone could enter negative age or invalid emails, which would corrupt the quality of the data. The entity integrity constraint says that every table must have a primary key, and this key can't be null. Why? Because the primary key is used to uniquely identify each row in the table. If we allow null values, it means multiple nulls will be allowed and replication is there. If the primary key were null, we would not be able to distinguish between rows. For example, in the student table, roll number is the primary key. Every student must have a unique roll number and it can't be left blank. This ensures that no two students can be confused with one another. The referential integrity constraint ensures consistency across related tables. For example, suppose we have two tables, program table having program ID, program name, and the student table having roll number, name, and program ID. Here, the program ID in student must exist in the program table. It means there is a concept of foreign key. In a student table, program ID is a foreign key. That's a primary key in another table, that is program table. If a student is assigned program ID 5, then there must be a program with ID 5 in the program table. This prevents invalid references like a student being enrolled in a non-existent program. It's like ensuring that every child in a school is linked to a real class that actually exists. If a student is assigned program ID 5, then the program ID is linked to another table, that's a program table. A key constraint ensures that certain attributes uniquely identify rows in a relation. These attributes are called candidate keys. From the candidate keys, one is chosen as the primary key. Other keys may also exist, such as foreign keys, which link relations together, as given in the previous table. For example, in the customer table, customer ID is a candidate key. We select it as the primary key. This means no two customers can have the same customer ID, ensuring uniqueness and consistency of table. The values of foreign keys can be replicated as we use any records multiple times. Now let's look at application-based constraints. These are rules that can't always be directly defined in the database schema, but they are still very important for maintaining data correctness. Instead, these rules are enforced by the application program that interact with the database. For example, a student's phone number can't have more than 10 digits. A student's age must be realistic, say between 15 and 100. A course load limit may state that a student cannot enroll in more than 7 courses in one semester. These kinds of constraints are usually business specific, meaning they depend on the real world policies of the organization. As in another given example, there is a table, namely employee, having employee ID as primary key. It must be unique. This primary key is, if we want to use another table, a department, having department ID department name, employee ID. Employee ID basically employee working in this department. So that's a foreign key over here and a primary key in employee table. So if schema based constraints are like the rules written into the constitution of the database, application based constraints are more like the school policies. They come from outside but still control what is valid or invalid. So next we have data dependency constraints. These include functional dependencies where one attribute uniquely determines another. For example, in a student table, roll number uniquely determines name, address and program. So in the employee table, employee name, age, IDs describe these. So in department table, department number and department location are the attributes. So over here in the department table, department number is the primary key, and in the employee table the department number is used as a foreign key. These key constraints are basically used for uniquely identifying the tuples. Then the application based constraints. Every relational database has a schema and a state. The schema is the blueprint of the database. It tells us what table exists, what attributes they have and how they are related. So in application based constraints that can't be directly applied in the database model schemes. So these are known as application based. For example, student can't have a phone number more than 10 digits. These are basically relevant. Then the data dependencies constraints. These dependency constraints belongs to the database after data insertion. We can't check at the time of modeling. However, we can fix that a phone number must be like in this format, date of birth like this format, roll number must be a 5-digit, 4-digit, having alphanumeric, etc. These all are called data dependencies constraints. Thank you for your attention, and I encourage you to review the examples and think about how these rules apply to real world databases. That's all for today. Allah Hafiz.